Deep foundations. When are they necessary? Welcome back to Blueprint to Reality, the channel where we dig deep into the engineering principles behind the world's most impressive structures. Today, we're taking that literally as we explore deep foundations. While shallow foundations may be common, sometimes going deeper is the only way to build safely. But how deep is deep? And when exactly do engineers decide that a deep foundation is the right choice? Let's dive in. What are deep foundations? Deep foundations are structural elements that transfer building loads to stronger soil layers or rock located well below the surface. Unlike shallow foundations, which spread the load near ground level, deep foundations bypass weaker or unstable soils and deliver the weight of the structure deep into the earth, sometimes dozens of meters down. They come in various forms, but all share one purpose: to reach stable ground when the surface soil just isn't strong enough. Why do we need deep foundations? There are several key scenarios where deep foundations become necessary. The most common is when the topsoil has a low bearing capacity. If a building's weight would cause too much settlement or risk failure on surface soils, engineers need to transfer those loads to more competent layers deeper down. Deep foundations are also used when structures are extremely heavy, like high-rise buildings, dams, or bridges. The site is in a flood-prone or seismic area, where surface soils may liquefy or erode. The soil is expansive or compressible, like clay that swells and shrinks with moisture. Space is limited and high-capacity support is needed in a small area. In short, when surface conditions are not reliable, deep foundations offer a secure alternative. Types of deep foundations. There are two major categories of deep foundations: piles and drilled shafts, also known as caissons. Pile foundations. These are long, slender columns made of concrete, steel, or timber, driven or bored deep into the ground. Piles work either by end-bearing, transferring loads directly to hard strata, or by skin friction, where the sides of the pile grip the surrounding soil. Drilled shafts, caissons. These are large diameter holes drilled into the earth and filled with reinforced concrete. Unlike driven piles, caissons are formed in place and often used in large structures like bridges and towers. Other types include screw piles, micropiles, and well foundations, each suited for specific conditions. Load transfer mechanism. Understanding how deep foundations work comes down to load transfer. In some cases, piles are driven until they hit a dense layer or bedrock. Here, they act like stilts, transferring load through end bearing. In other cases, especially in cohesive soils, piles use skin friction, the resistance between the pile surface and surrounding soil, to support the load. Often, both mechanisms work together. Drilled shafts follow a similar principle but allow for larger diameters and more customization. They're particularly useful when dealing with heavy vertical loads and lateral forces, such as in earthquake zones. Installation techniques. Deep foundation installation is more complex than shallow foundation work. It typically involves heavy equipment and skilled labor. For driven piles, large hammers or vibratory equipment drive preformed piles into the ground. This method is fast and effective but can cause vibration and noise, which is a concern in urban areas. For bored piles or drilled shafts, a hole is first excavated with rotary drills. A reinforcement cage is lowered into the hole, and concrete is poured to create the pile in place. Sometimes, temporary casings or bentonite slurry are used to prevent the hole from collapsing before concrete is poured. Advantages of deep foundations. Deep foundations offer several critical benefits. They allow construction in weak or problematic soils. They can support very large vertical and lateral loads. They reduce settlement issues, improving the stability of tall or heavy structures. They can be used underwater or in marine structures, such as ports and offshore platforms. Essentially, deep foundations unlock the ability to build anywhere, regardless of what's beneath the surface. Limitations and challenges. However, deep foundations are not without challenges. They are more expensive than shallow foundations, require advanced machinery and skilled labor. Installation can be disruptive in populated areas. They demand detailed geotechnical studies and careful design. Moreover, poor installation or unexpected soil layers can lead to issues like pile buckling, heaving, or misalignment. That's why site investigation and quality control are absolutely critical in deep foundation work. Real-world applications. Deep foundations are commonly used in skyscrapers, where loads are too large for surface soils. Bridge piers, where water and soft sediments require deep support. Wind turbines, which need strong lateral resistance. Industrial complexes, power plants, and transmission towers. A great example is the Burj Khalifa in Dubai. This 828-meter-tall structure stands on a deep foundation system using more than 190 board piles, each extending up to 50 meters into the desert soil. Without deep foundations, such a building wouldn't be possible. Conclusion: deep foundations are the hidden giants beneath our cities, silently bearing the weight of progress. They allow engineers to build higher, stronger, and more safely, even when the surface tells us we shouldn't. Whether it's supporting a massive bridge over a river, a tower reaching for the clouds, or a stadium packed with thousands, deep foundations are there, unseen but essential. Thanks for joining us today on Blueprint to Reality. If you enjoyed this dive into the world below ground, subscribe for more no-visual, all-value engineering insights. Until next time, keep building smart.